All right, so let's go through. I have a line charge here. So a line charge with uniform linear charge distribution. And I'll use lambda for that. So that is equal to, well, in essence, charge over length. But let's go ahead and make this infinitely long. And so it doesn't really make sense to do Q because it would be infinitely large. However, we can look at a smaller part of it, dq over dl. Now, if I just go ahead and make sort of that is my x direction, then we can also write that as dq over dx. And it might just be a little bit simpler to do the derivation in terms of x instead of L. So not a huge loss there. Matter of fact, there's no loss there. Arose by any other name. So I want to figure out what is the force on a point right here. So I have a point charge Q, and I want to know what is the force there. This distance right here, we will make a distance, we'll call that big R right there. So generic steps is I need to pick some differential here. I set up a coordinate system. And I'm going to call this dq. And this distance right here is little r, and this is big R. Now we are dealing with vectors, so we do need a temporary angle here. So I'm just going to create an angle here, and I'm going to call that theta, because I'm clever. Because I am brainwashed. So, and this distance right here is x. I'm going to make that x is equal to 0 there, and so this position right here is x. So the force at this particular point, so the force is equal to kq dq, I guess that's df, over r squared. And again, we are left with a situation here of, I know that force is going to be in that direction. I have one over here. There's going to be some part over here which has a force in the sort of symmetric opposite direction. And so the only thing that survives is that which is that is perpendicular to the line here, to the line of charge. So let's set up a coordinate system here. We'll call that I hat and j hat. So the j hat is the only part that is going to survive. So since the j hat survives, I need a component here. If this is theta right there, that angle there is theta, and so the part, this becomes cosine of theta j hat. Sine of theta j hat. So sine is that part right there. And so, well, we now have 1, 2, 3 variables here. So we need to get this all in terms of a single variable. And so F equals KQ integral dq over r squared sine theta j hat. Oh, j hat can come out. J hat. I know the linear density here. So let's sort of start on that one. And that's a q. So from here, I have dq is equal to lambda dx. And so this becomes j hat k little q integral lambda dx over r squared sine theta. Again, looking at our triangle there, my dq is right there. This is where little q is. This is my origin. So this distance was x. This is little r, and that's big R. Well, I have a relationship between big R squared, and that angle there is theta. I have a relationship between these variables right here. I have dx is my differential, and so let's see if we can get little r in terms of that. So I know that little x squared plus big R squared equals little r squared. Sine of theta, again, I have the relationship here, is big R divided by hypotenuse, little r. So whichever one I want to do first. Let's do j hat k q integral, lambda can come out. So dx over r squared, sine theta is big R over r. I have big R that can now come out, so this becomes j hat k q lambda big R dx over r cubed. Well, I know what r squared is equal to, so this becomes j hat kq lambda big R integral dx over, well, if r squared is equal to that, if I do raise both sides to the 3 halves, I get r cubed over here. And so what I'm left with is x squared plus big R squared to the 3 halves. I now have it in terms of a single variable. Well, what are the values for x? Since this is infinitely long, my dq can go anywhere out there or anywhere out there. So basically it's going to be going from negative infinity to positive infinity. So negative infinity to positive infinity. And that is the math problem. Now the question comes down to, how do you solve this? I'll give you a moment to think about how to solve it, and then I will talk about the engineering method, or sorry, the physics method of solving it. I'm assuming that you have either paused it or just kept going, but if you paused it, welcome back. And if you just kept going, then I'm hoping that you already knew how to solve it. So the physics way is to look it up. And so here's a table of integrals right here. And looking at number 48, I think it's standardized. I'm not 100% sure of that, but I think it's standardized. So this is basically the integral that we're dealing with, the positive denominator instead of the negative sign in the middle. And according to it, so the physics way is to look it up. And this is the table of integrals. This one right here is the one that we care about, where n is equal to 3 halves. And so if we write that out, and we really only have to do this one time, because after that, this formula is pretty much given to you, over c squared plus x squared to the 3 halves. So that's n is equal to 3 halves. And again, looking back at this, it gives plus or minus, and we're just looking at the positive one, because that's what our formula is. We got positive there. And that's 1 over 2c squared n minus 1 times x over c squared plus x squared to the n minus 1 plus 2n minus 3 times the integral of dx over c squared plus x squared to the n minus 1. Now this might seem daunting at first, but if you, since n is equal to 3 halves, this right here becomes 2 times 3 halves minus 3, or 3 minus 3, or 0. This whole term drops out. And so what we're left with is this nice little bit right here. Our formula for the force being in the j hat direction, k, q, lambda, r, integral negative infinity to infinity of dx over x squared plus r squared to the 3 halves. That becomes r, big R and c are the same thing here. So this becomes 1 over 2 times big R squared times n minus 1, which is 1 half. Again, n is 3 halves. Times x over r squared plus x squared to the n minus 1, which is n minus 1 becomes 1 half to the 1 half. So it's basically over the square root of r squared plus x squared from negative infinity to infinity. So this becomes, oh, and that whole bit up front. So I get j hat k q lambda big R over, those cancel out. So I have this r over r squared here. And then I plug in infinity. And so I get infinity over the square. Well, let's do it slightly more sophisticated than just the hand wave that I typically do on this. I'm going to factor x squared out. So this becomes x over, factoring x squared out, I get x times the square root of 1 plus r over x squared from negative infinity to infinity. I plug infinity in, this term goes to 0, and so I'm left with x over x, or 1. I plug in a minus. I plug in a negative infinity, and again, this term goes to 0, and I get negative infinity over, this would be the absolute value of x. So I plug infinity in, and I get infinity over infinity, because this term right here goes to 0, and so I get 1. I plug negative infinity in, and I end up with negative 1. So I end up with j hat k q lambda over r times 2. Or in more traditional form, 2kq lambda over r. And so that is in the j hat direction. In other words, in the direction perpendicular to the line itself, that is the force from an infinite line of charge. If it's not an infinite line of charge, then what changes are the limits of integration here. But you can handle that, just plugging in different values. If we used the other form, instead of k, did 1 over 4 pi epsilon sub naught, because sometimes epsilon sub naught, sometimes you'll see that as well. So if I plug that in there, the 2 and the 4 will have some canceling, and I'm left with q lambda over 2 pi epsilon sub naught r in the direction perpendicular to the line. That would be the force.